Hi everybody, Ms. Tobin here. We're going to be doing a video with some examples on a process called partial fraction decomposition, which is no doubt a pretty intimidating title. The actual process is definitely easier than the title makes it sound. So what we're going to do is start off looking at a question that we did a couple sections ago back in P.6, where we want to perform subtraction and they don't actually have like denominators. So I'm going to ask everyone, pause the video, go ahead, give this one a try, see what you come up with. All right, so we have got here a least common denominator of the quantity x minus 4 times quantity x plus 2. So we're going to go ahead and match those. So the one on the left, we're going to give an x plus 2 over x plus 2, keeping that equivalent to 1. For the one on the right, we're going to make sure to multiply that by x minus 4 over x minus 4. Note, again, this is just a expression. It's not an equation. I'm not doing something like both sides of the equal sign or anything like that. I am just trying to subtract these with a common denominator. So once I have this, we'll have 3x plus 6 over, I'm just going to keep the denominator factored in case anything simplifies later. Subtract 2x minus 8. And now we have that common denominator. So we know 3x take away 2x should just be x. Keep in mind that I am subtracting a negative 8, so I'm actually adding 8. So we should wind up with x plus 14 over x plus 2, x minus 4. And I know that there is nothing that simplifies here. So I am just left with this as my difference, right? That is my resulting answer here. So we've done a lot of these where we've looked at maybe two or more rational expression terms and we've operated on them, right? Maybe we added them, maybe we subtracted them, really same thing. And then I'm looking at my resulting answer. What was my sum? What was my difference? So what we're going to be doing in this video is essentially going backwards. We're thinking about what if we were just given this final difference or this final sum, and we're thinking about, well, what would be maybe two simpler individual fractions that we could have put together in order to get that as our resulting answer. So we're really just trying to think, what is it that we could add or subtract to get this as an answer? Now, in this case, we obviously know, right? We were literally given these two, and we got our final answer. The question is, what if I just have that sum, and we have to come up with what those original fractions were? And that's what we're going to be looking at here. Okay, so this is the first example that we're going to be doing. We should be seeing right off the bat that on my right side, I have this x minus 5 and this x plus 1. Those are the factors of my original denominator. So what we're thinking about is that this here, 5x minus 13 over, we'll just factor that, x minus 5, and my factor x plus 1. This is essentially my sum. You want to think of this as, this was the answer to one of these questions that we had in P.6. And the question is, well, what did we add up to get that as a final answer? So we're going to look at those two different factors in the bottom, the x minus 5 and the x plus 1, and think about, we'll have had some constant over x minus 5 and some constant over x plus 1. And I'm going to encourage you right now to, again, pause the video and think about what might you do to find out what those unique constants A and B are. All right, so there's a couple different ways for us to think about it. One would be to just get this common denominator here. So think about multiplying by x plus 1 over x plus 1 and x minus 5 over x minus 5. And now that all of my denominators match, we know that logically this equation must hold true as well, right? And keep in mind, back when we were doing these solving rational equations, we would have gotten the exact same equation here should we have multiplied by that least common denominator. So we're left with this equation. I'm just expanding it out here. And it looks like we've just got this whole big mess of A's and B's and X's and everything. And what we've got to do is figure out what is it that A and B are. What are they equal to? So we start to just kind of match the different terms. So I see on my left side, we've got a 5x. On my right side, we've got an ax and a bx. And so, if we know that 5x is ax plus bx, that tells me that ax plus bx has to match to 5x. Or we could think of it as those coefficients added up have to sum to 5. Okay, and then similarly, we know that a minus 5b, since I don't actually have an x variable attached here, have to sum to negative 13. So either a plus negative 5b or a minus 5b, my resulting answer here should be negative 13. And at this point, now I just have a system of equations. I've got two equations, I've got two variables. We can go ahead and solve this. So we could do substitution if we wanted. I'm going to go ahead and just solve this with elimination. So I'm going to change all of the signs here and then just add them up. So a plus negative a is 0. We'll wind up with 6b here. 5 plus 13 is 18. That gives me that b is 3. And then since we knew that a plus b was 5, that'll give us that a is 2. And so that means going back to our original breakdown here, we have a, which is 2, over x minus 5, and b, which is 3, over x plus 1. And if we had any doubts, we could definitely add these two up, make sure that we do in fact get that sum as our 5x minus 13 over the aforementioned quadratic. So what we have here is what's known as the partial fraction decomposition. So each of these are considered partial fractions. And I can think about the fact that my numerator and my denominator don't have any common factors. Right? 2 over x minus 5, that isn't going to simplify. Same with 3 over x plus 1. So these are both the partial fractions. And then the decomposition just means we essentially decomposed what our final result was. We went back and figured out what was it that we needed to put together in order to get that end result. So if we look at the very first question that I had asked you to subtract. So back in the beginning, we did either, we can think of it as adding the negative 2 or subtracting our 2 here. And we knew that this resulting difference was x plus 14 over our quadratic. So what I want us to do is think about, what if we didn't know this, right? What if we didn't know that we had a 3 over x minus 4 and a negative 2 over x plus 2 that we were adding together? What if all we had was our x plus 14 over x squared minus 2x minus 8. So first thing I'm going to do is see, can I factor that denominator, which we know that we can. So we have x minus 4. Make that a little smaller. And x plus 2. All right. So what we're going to do is break this up where we have some constant over x minus 4. We'll call it a. some constant b over x plus 2. Important to know that it wouldn't have mattered if we had these denominators in a different order, right? Addition is commutative. I could have put the x plus 2 first and the x minus 4 second. This is especially important for when you're comparing your work with somebody, because you don't want to be thinking like, oh, I got A as 3, and the other person say like, oh, I got B as 3. Well, maybe you just wrote your denominators in the opposite order. Right? If that's the case, then your A and your B values would have been swapped. So in this case, I'm assigning A to be the numerator over x minus 4, B over x plus 2. So now that I have that, we're going to concentrate on this equation here. And we'll do it a different way than we did on the previous example, just so that we can see both of those visuals. So here, I'm going to multiply through by that original denominator. So I'm going to multiply my left side by x minus 4, x plus 2, and my right side. I like writing it twice so that I can physically cross it out. That's a minus 4. X plus 2 times x minus 4. So we'll see here our full denominator cancels, x minus 4s, and the x plus 2s. And what we're left with is our x plus 14 equals x plus 2 times a and x minus 4 times b. Again, I would have got the exact same thing if I had just concentrated on matching those denominators and then focused on my numerator equation. So I'm going to expand out by multiplying through by that a and the b. So we'll have x plus 14 equals ax plus 2a, bx minus 4b. Now we start matching. So we're thinking we have just got a 1x over here. But on my right side, I have ax and bx. So we could write it all out with the x's if we want. I know that the sum of my coefficients is going to have to be 1, since ax plus bx gave us 1. Similarly, now we'll look at the constants. 2a minus 4b is going to sum to be 14. I can solve this any way that I would like for systems. I'm going to multiply the top one through by 4 so that we can write it as 4a plus 4b equals 4. And then just go ahead and subtract, or not subtract, excuse me, add our second green equation. So our 4b's will cancel out, and we are going to have 6a equals 18, a as 3. Now, if I know a is 3, and I know a plus b was 1, 3 plus b is 1, b is going to have to be negative 2. Okay, and so now if we look back to that original, my original rational expression up here, we had 3, our a value, over x minus 4, and negative 2, our b value, over x plus 2, right? Keep in mind this is the exact same thing as if I'm just adding a negative 2. And so what we've done is decompose this sum to find those individual partial fractions. Okay? So the big thing that you'll see if you look through the textbook for this section is there are multiple cases. And I've highlighted here the only case that you're going to be held responsible for this honors pre-calculus course, which is case 1, exactly what we've looked at so far. The denominator has unique linear factors. Unique meaning that they are not repeated. So I don't have the quantity x plus 2 squared, right? I don't have an x plus 2 and another x plus 2. They are not repeated, and they're all linear. All of those factors for the denominator came down to like x plus 4, x minus 2. I didn't have any irreducible quadratics. Now, you can see here, there are obviously other cases. So maybe I have something like a linear factor of x, but it's in there twice. Okay? Your setup for this is going to look a little bit different. Same thing for case 3. If I've got a factor that's an irreducible quadratic, meaning I have a quadratic factor, but I can't break it down into linear factors, that skeleton for the decomposition is going to look a little bit different as well. Right? And then I could have further cases where I start to combine case 2 and case 3. Right? And this is technically quadratic or higher. So while there are several different cases for our particular course, and if you choose to take an AP Calc option at our school, the only case that you are going to be assessed on is case 1. So where we have these unique linear factors. However, they might pop up in future math classes in your math career, so I want to make sure that we are exposed to them. You can always go back. Your process is going to be the same. It's just that your initial setup is going to be a little bit different, so keep that in mind. But we're going to go back to just case 1 here. All right, first things first, I'm going to encourage everyone, pause the video, go ahead, give factoring that denominator a try. All right, we can do a little bit of side work over here in purple. So 2x squared minus 5x minus 3. I need numbers that multiply to get my product of -6. Add to get -5. So our numbers are going to be -6 and +1. We're going to use those to then split up that middle term. So we have our 2x squared. We have our -3. It's just instead of writing -5x, we're going to write -6x plus 1x, and then we'll factor this by grouping. Remember that I'm taking out a 1 factor. You don't want to just write nothing here. It is a +1. So we wind up with 2x plus 1 and x minus 3 as our factors here. So notice, just like we said before, this is case 1. We've got it broken down into factors that are not the same and they're linear. So we'll have 7 over 2x plus 1, x minus 3 equals something over 2x plus 1 and something over x minus 3. Okay, up to you how we get to that linear equation. I'm just going to give this an x minus 3 over x minus 3 and a 2x plus 1, thanks, over 2x plus 1. Okay, so I want everyone to keep in mind, it's not that we're getting rid of the denominators, it's just that we're focusing on the numerator. If we know that we added those two terms on the right together to get my left side 7 over, that means that this equation is going to have to be true. My denominator's matched. So we have 7 equals ax minus 3a plus 2bx plus b. And what's a little bit different for this one than perhaps some of those earlier questions is that this is a 0x plus 7. I don't actually have any x's on the left side, so that's something to keep in mind. Because when we go to set these up, I've got no x's, but on the right side, I would need to combine ax plus 2b. So we have 0 equals a plus 2b, and we'll look at our constants. 7 equals -3a plus b. Okay, solve this any method of your choosing. I'm just going to multiply the top one through by 3. So we've got 7 equals 7b. B will have to be 1. And then I can go back to either of my equations here. So if we've got 0 equals a plus 2 times 1, we know that a is going to have to be negative 2. Okay, once you have found those a and b values, you are not completely done yet, though. We do want to make sure that we are providing our final answer. So we're saying that our decomposition here, which was our a value over 2x plus 1, and our b value over x minus 3, and make sure that we've got them corresponding back to whatever we had originally here. So we had a over the 2x plus 1 denominator, so that'll be negative 2. Oops. And then our b value, which was 1, over x minus 3. And that is partial fraction decomposition.